Hi everyone, I'm Emily Joback and I'm from MIT Lincoln Laboratory. Today I'm going to be talking about a work that was done on detecting low throughput exfiltration through the domain name system. An organization's network data can contain tens to hundreds of thousands of domains a day. With such a large dataset, it's obviously not possible for a network analyst to go through each of these domains to determine which are a threat. So the goal of this analysis was to develop a tool which would aid the analyst by sifting through the domains and highlighting only a handful of suspicious ones that the analyst would then need to consider. By doing this, we're reducing the analyst's workload and allowing for detection of malicious activity that would have otherwise have been hidden within all the benign data. So before delving into our analysis, I quickly want to introduce the domain name system and how this protocol works. So this protocol is what makes it possible for us to be able to type a human-friendly URL string, such as google.com, into our browser, instead of having to remember the IP address for that website. When you type in that URL string and hit enter, that request is taken care of by a DNS resolver. The DNS resolver forwards that request to a root server. So a root server is what is responsible for all of what is known as the top-level domains. So the top-level domain is the very ending of that URL query string. So in the case of google.com, it's the com portion. There's obviously other top-level domains such as edu for education or .mil for military. And I believe in total there's a little over 1,000 different top-level domains. So this root server takes the request for google.com, and it doesn't have the IP address for google.com, but it does know the IP address of the host responsible for all the .com addresses. So it sends that IP address back to the DNS resolver. The DNS resolver takes that IP address and goes to that top-level domain server responsible for .com, and that top-level domain server knows the IP address of the server responsible for google.com, so it sends that IP address back to the DNS resolver. So finally, the DNS resolver goes to the domain level name server responsible for google.com, and that server sends back the IP address for www.google.com. One thing to note is that this example is the iterative method of the domain name system. There's also the recursive method, which is very similar, but instead of the DNS resolver receiving the response back at each step, the resolver hands off the responsibility to the DNS server, and then the DNS server queries other DNS servers to get the IP address for google.com. And then that DNS server then responds back to the DNS resolver with either the correct IP address or an error if it was unable to find it. So one thing I really want to stress is that DNS is a critical component of the web, so this protocol needs to be extremely reliable and timely with its responses. This protocol can't just be shut down without breaking the web, so this makes the protocol an ideal tool for maliciously transferring data. So that leads us directly into how the protocol is abused for data exfiltration purposes. A malicious actor registers a domain name. In this example, we're using badsite.com, which they then query from a compromised machine within a network containing data they like to steal. That data is encoded and placed at the beginning of the query string, and through the DNS protocol, the full query string is sent to the server controlled by the bad actor, who can then decode the data. So as I mentioned previously, the DNS protocol is a critical component of the web, so there are very limited security measures enforced on this protocol. In addition to this, since it was never designed for the purpose of data transfer, it isn't monitored as closely as other protocols such as FTP. Specifically for this project, we're looking at the case where data is transmitted in small amounts over an extended period of time. And in doing this, an attacker circumvents conventional tunneling detection algorithms, which look to flag high-frequency data transfer. Because of all of this, this is an increasing method of attack. One very well-known example was the case a few years ago where Home Depot had information on 56 million credit cards from their customers stolen using DNS exfiltration over the course of several months. Early research in this field focused on detecting specific tunneling tools, such as iodine or TNS to TCP. The focus then shifted to applying machine learning techniques to any type of tunneling. More recently, work has been done on detecting low-throughput exfiltration, the kind of attack which is used on Home Depot. However, Current research on the low throughput exfiltration requires a curated dataset and training a model. Supervised machine learning requires a labeled dataset of good and bad data, and the most recent approaches with one-class classifiers required a clean dataset of good data. Both approaches require training a model, which is something which must be tuned over time as the network evolves. Therefore, there is a need for a model which can be applied as is to a network without requiring training on a curated dataset. So the data that we used in our analysis was collected from LONOC, which is an enterprise research network containing real network traffic from our organization. This dataset spans a 2-week period in March of 2017 and contained over 111,000 domains. For each of these DNS logs, which I'm showing an example at the top of this slide, we extracted the query string, which in this case would be maps.google.com in our example, the source and destination IP, and the query record type. We then separated the query string into subdomain, which would be the maps portion, domain, which would be the Google portion, and the top level domain, which would be the com portion. And then for each day, we would group by domain and top level domain pairs. So for the example of Google, you can imagine that the string would contain maps and doc and keep, which are all part of different queries that would go to google.com. And this process was repeated for each day in the dataset. We also generated synthetic exfiltration data. We did this with the purpose of mimicking the attack on Home Depot. Although I do want to note that this synthetic data was only used as a comparison to the results we saw from our actual network traffic data, and not for training a model. As I described in the previous slide, for each domain we have these concatenated subdomain strings, which are updated for each day in the dataset. For each of these concatenated subdomain strings, we're calculating 10 different features, which I'm showing in this table here. So for example, one of the features that we're looking at is the average length of the subdomain. Since the purpose of the attacker is to exfiltrate data, you would expect the subdomain of a query to be longer than the typical subdomain length for a legitimate website. Another feature is the character entropy. So this is measuring sort of the randomness in the concatenated subdomain string. We would expect the exfiltrated data to typically be encoded, so the characters would appear more randomly assorted compared to a normal English word, which might be seen in a typical subdomain of a legitimate website. So in this slide here, I'm now showing the distributions over the 2-week period for each of these 10 features that I described in that table. So I won't get into each individual distribution, but the purpose of this is to show sort of the expected values for each of these features. And the point of that is that we would expect a suspicious domain to have one or more features whose value is an outlier compared to the majority of the data set. One of the features is the alphabet ratio, and we see that on average, over half of the domains on a given day have a value equal to 1. That means the entire subdomain length is all alphabet characters. That's not surprising. When you typically type in a URL string in your browser, you don't typically type in numbers. It's usually alphabet characters. Another feature that we looked at was the upper ratio. This is looking at the ratio of characters within your URL that are capitalized. And we can see that in this case, for our data set, almost all the points that we're looking at have a ratio equal to 0. This means the majority of our DNS queries contain uncapitalized letters. Now that we have all these features that describe our dataset, we want to be able to visualize these points. We did this by using dimensionality reduction, which I'm showing the notional results of in the figure on the right. Each of these points represents one domain per day, where again, I'm using google.com as an example of a good data point. Because we've chosen features which we expect to relate to data exfiltration, the theory is that outliers that we detect in this plot correspond to domains which are exfiltrating data. As we see in this notional plot, the point for badsite.com is well separated from the rest of the good data. So the dimensionality reduction technique that we used was the principal component analysis, This is very commonly applied in statistics for reducing dimensionality while being able to detect outliers. And the reason for this is that it chooses the orthogonal coordinate system for data where the axes are along the dimensions with the highest variability. One thing that we did was a quick check to confirm that our principal component space was consistent between consecutive days, since we're recalculating the data each day and then recalculating the principal components each day. And the analysis for that is described in more detail in the paper. So here in this slide, I'm showing the results for one of the days in our data set. This is for a Tuesday, and this is showing the first two principal components across the data points using those 10 features that we discussed previously. We saw that using just the first two components in principal component analysis still maintained greater than 99% of the variability, so we're still capturing the differences between data points while being able to represent it in only two-dimensional space. One thing that was interesting to note was this sort of stratification behavior that we see in this plot. So you see that a lot of the data points tend to be grouped in those vertical lines. And when we investigated this, we saw that the biggest driver seemed to be the length and the entropy of the subdomains in the each of those shared vertical clusters had similar values for those two variables. Once we had calculated the principal components and plotted the data in the first two dimensions, we wanted to then see which of the 10 features were the biggest drivers for where a point was within this plot. This left figure shows the correlation between each of these 10 features with the first and the second principal components. So we can see that the second and the third features are the most important out of all of the 10, which are the average length and the character entropy of the subdomain strings. Both of these I described earlier when I first introduced the features. But one thing I'd like to note is that, while those two are the biggest drivers, there's a non-negligible contribution from most of the other features as well, so we can't just use those two features to describe our data. The whole purpose of using principal component analysis was to be able to see which of our points were outliers. We're expecting that a point that represents DNS exfiltration has an abnormal value for one or more features, so that the outliers in our data represent the exfiltration points. In the plot on the right, we're showing the data points for a Thursday in our dataset in the principal component space. You can already see by eye that there are some clear outliers, but we're using the Mahalanobis distance to determine which were the actual outliers. These are shown by the red circles. Yellow circles represent our injected DNS exfiltration data as a comparison to the points in our network data. We can see that they also lie in the outlier region of our plot. The table on the left lists some details on the two outliers which are furthest out. We can see the subdomain string is not something we'd expect to see as a query from someone typing a URL into a browser. When we investigate these domains further, we found that they were general service lookups, so not malicious, but they do in fact use the DNS protocol to transfer data. The fact that our algorithm detected these as outliers gives us confidence that we can use this visual aid to help detect suspicious domains which should be investigated further by network analysts. Now that we can detect outliers in the dataset, the next thing we wanted to do was to baseline the data. By doing this, we can see changes in the behavior of a domain, which is expected in the case of low throughput exfiltration over time. Our approach for this is to identify clusters in the data and then see if domains switch clusters between days. We initially tried clustering using common clustering methods, and those are shown as the 3 panels here. So on the left we have k-means, in the middle we have the results from dbScan, and then on the right we have the results from mean-shift. Of the 3, you can see that mean-shift did the best job at capturing that vertical stratification behavior we see in our dataset. However, it was not ideal still, so our approach was then to engineer a new way of clustering our data, as we decided that the classical clustering methods were not effective at capturing the stratified behavior that we see in our data. To determine our clusters, we started by binning the data points in the x dimension to get the density of data within that axis. So that's shown as the first step here, and the data density in the x direction is shown as the bottom left plot. We then identified the peaks for the density, and that's shown as the bottom middle plot, and those red points highlight the peaks. And then we use those peaks to then decide what the middle of each cluster is going to be. And then that was how we determined our clusters. And as an example, we're showing the top 20 clusters resulting from this method for one of the days in our data set. Now that we have a way to identify these clusters, we wanted a way to compare the domains in each cluster between consecutive days and highlight which domains changed groups. To visualize this, we're using an arc diagram shown in the left of the slide. Each of the nodes, or circles, represents clusters on 2 consecutive days. So for example, the 2 leftmost nodes represent cluster 1 on day 1 and cluster 2 on day 2. Similarly, the 2 largest nodes represent cluster 2 on the first day, and then that same cluster again on the following day. The edges connecting these nodes represent domains which switch from one cluster to another cluster between the consecutive days. We've weighted the connection by how far apart the clusters are that the domains switch between, as we want to really highlight points that move far within that principal component graph. But then we're normalizing that value by the number of domains that made that same switch. If a lot of domains exhibited the same behavior, it's likely normal. The domain called out in this figure, represented as the maroon line and pointed out as domain 4512, is the edge with the highest weight in this example. And in this case, this domain switched from cluster 3 on the first day to cluster 25 on the second day. At the bottom of the chart, I'm showing a summary of some of the important features for this domain that we're looking at, as well as an example of one of the subdomains that was seen in the query for this domain. And what we found is that when we looked into this domain a little bit further, this domain was seen to only have a couple of queries on some of the days, and all those queries were just www.thisdomain. And then on other days, when it made this jump, the query suddenly looks like that long string that you see, which kind of seems almost like something that could be encoded, and that was attached to the domain, and it went from only a couple of queries a day to several hundred queries a day. So this is definitely an example of suspicious behavior by a domain that we would want to flag for an analyst to take a look at. It's just a quick check on using the clustering and arc diagram analysis to detect if a domain moves from its normal position in the principal component space. If we were to find that the majority of the domains were actually bouncing between clusters each day, it would then tell us that this isn't a good approach for detecting outliers within our data. The plot on the right shows the results, where the x-axis is the clusters the domains belong to for the first day, and the y-axis shows the clusters the domains belong to on the following day, for each consecutive set of days in the 2-week period that we're looking at for our data set. We can see that the strong response is along the diagonal, so that means that domains tend to remain within a given cluster. So this tells us that our approach is valid. So this chart is just wrapping up the analysis that we've done. It's showing the 2 different metrics that we've developed for detecting domains that may be performing DNS exfiltration. The first is that straight up outlier detection using the principal component space. The second is then the arc diagram that highlights domains that have changed their location within that principal component space from day to day. And the final tool that we would develop would look at taking the list of suspicious domains from each of these approaches and aggregating them into a list for a network analyst to delve into deeper to determine if these domains are performing malicious exfiltration and need to be addressed. One thing that can be applied is a filter to check for whitelist domains, as if you have a domain that is approved by a network analyst to be benign, you don't want them to have to continually see that as a domain that they need to investigate every day. And then once that whitelist is applied, you can then output your final list for the analyst on a given day of domains that they need to consider that might be performing DNS exfiltration. So this method has helped significantly reduce the analyst workload by decreasing the number of DNS queries to inspect by several orders of magnitude, because we went from 10 to hundreds of thousands of domains to now only a handful of a few domains that they need to consider. So in conclusion, the DNS protocol can be manipulated to exfiltrate data out of a compromised computer within a protected network. And this type of attack has already been used very effectively against multiple large companies. We've developed some analytics which can detect this type of low throughput exfiltration through DNS. And this analytic that we develop could be something that's used by a network analyst to determine a handful of potentially suspicious domains rather than having to sift through hundreds of thousands of DNS queries.